Okay, class, we're about to start section 2.6. Now, in section 2.6, it's only 2 pages that we're going to do. It's on pages 188 and page 189. So let's take a look on page 188. Number one, the equation y equals 81.15 times 1.013 to the x can be used to model the population of the United States in millions of people based on the number of years since 1900. Identify the variables and parameters in this equation and describe what the significance of each is in terms of population. Now, the reason why I'm having us do this problem is to give you a basic overview of the exponential decay and exponential growth. So we know that the formula is y equals ab to the x. That's our typical formula. So now our variables here, our variables are y is equal to the population of the US in millions, and then x is the number of years since 1900. Now they ask us for the parameters. So now when they're talking about the parameters, they're basically asking us what is A and B. That's what they're really asking us. What is A and B equal to? So I'm gonna have to write up here. I kind of didn't give myself enough space, but I'm going to write it up here, the parameters of this problem. Is that the first parameter is the 81.15, which we see. Look like it's auto adjusting. Okay. Is the 81.15, which we see here. The 81.15 tells us the US population in 1900 was about 81.15 million. Because remember, our A is our starting value. And since the year is 1900 is our starting value, that is telling us that 81.15 is 81.15 million. And that was in 1900. Now, the 1.013 is the growth factor. That tells us the population grows by about 1.3% each year. Now, one easy way you could tell whether something is growing or whether it's decaying when you're looking at the formula, if what's in the parenthesis is above 1, that means that it's growing. If it's below 1, that means that it's decaying. Does everyone follow that? Okay. All right, so now we'll go down here to number 2. It says use the equation in question 1 to complete the table. Then use the table to draw a graph of the equation. Don't forget to label an appropriate scale on each axis. Now there's a mistake on my course pack. I don't know if it's a mistake on your course pack or not, but it says years after 1980. We're supposed to be doing 1900. So change that 1980 to 1900. Okay, now the 0 year, which would be 1900, we already know is 81.15 because this population is in millions. Now we need to find out what 20, 40, 60, 80, and 100 is. So this is where we would do our Desmos calculator. you could basically type in the equation y equals the 81.15 times 1.013, and we would take that to the x power. Okay, so now we have our equation. We could click on this wheel here, click on the table, and you notice here we have this table of values. So now all we have to do is type in the numbers that are shown here. So we type in 20, and we will round to 2 decimal places. So this will give us 105.07. Type in our 40, and that'll give us 136.04. Then our 60, 176.14. The 80, 228.06. And then finally 100, and be 295.28. Now they also want us to graph this. If you look down here, this will be our 0 points for each one. So this is 1, 2, 3, 4, and then if you notice here, this is the longer tick mark. So everything is going by 4s. So what I will propose is that we go by 5s for each tick mark. So it'd be 5, 10, 15. This would be 20. This would be 40, 60, 80, 100, and then 120. Okay, now going up the side here, the population, if you notice, the lowest of our population is the 81.15. The highest is 295.28. So we need to get up to at least 300 in order to have a good graph here. So going up here, we got 1, 2, 3, 4, 5. We're going by 5s here. I think we should go by 10s. So this will be 10, 20, 30, 40, 50. Then this will be 100, 150, 200, 250, 300, 350. So we have more than enough space here to graph. Now we want to graph these values. So from 0, it'll be 81.15. So we were going by 10s. So this is about there. Okay, then we have 20, say 105, say about here. Then we have 40, 136, so 10, 20, 30. So it'll be about here in the middle. Then we have 60, let me see, 150, 60, 70, almost 180. Then we had 80. Let me see, we had 200, 10, 20, a little bit before 230. Then we have 100, will be a little under 300. Now, we connect these points here. And this is our graph. Now for number 3, it says the equation y equals 81.15 times 1.013 to the x illustrates exponential growth. The population was growing by 1.3% per year. The model used in questions 1 through 3 was obtained using official data for every census from 1900 to 2010. The census is conducted every 10 years. Use your model to predict the population in 2015. Then find the population of the United States in 2015 online and compare it to your result. Okay, so we have our model, y equals 81.15 times 1.013. We'll take that to the x. Now, they want us to go to 2015 from 1900. So that'll be 115. So we could go right back over here to Desmos and type in 115 for X. And that'll give us 358.41. And we know that'll be million. Okay, so now I would tell you what they have online. Online, they had a population as 325.13 million. So our prediction was high and over 30 million more people. Over 30 million more people. So our prediction was very high. Okay, now we move on to the next page. It's page 189. It says, what do you think the result of your answers to question 4 say about population growth in the 21st century? We could say that the population growth has slowed down. Has slowed down. So the model needs to be altered to stop over predicting. Yeah, they need to get a new model so it will stop over predicting. Now it says, what if we use only more recent data? Since the census is conducted every 10 years, we'll have to use a different source. I use estimates from a site called Worldometers, which are based on multiple data sources that are likely to make them more accurate than the census. In fact, the census is historically not the best measure of the true population for a wide variety of reasons. The table below has data for years from 1900 to 2010. Use the data to find the exponential equation of best fit. Include 5 digits in all parameters. Note that X now represents years after 1990. Okay, so first of all, we have our 0 year. Now we know we have y equals ab to the x. We know that a is our 0 year. So it'd be 254.51. So what we need to do now is find out what b is equal to. Now, we may have to change this. As a matter of fact, yes, I'm going to change this because we could just use the calculator. So let's use the calculator. So what I'm going to do is add a table here. Let the calculator do the figuring for us. So we will have 0, 5, wait a minute, I put 5, 10, let me see, 15, and then 20. Okay. Now we have 254.51. Let's see, 268.04. Let's see, 284.59. 298.16. 312.25. All right, so now we have all of our figures in. So we can use the calculator to determine the exponential growth. So we would do exponential regression here. So we know our formula is y And I'm going to type this in here. Y equals AB to the X power. We know this is the formula that we're actually searching for. But to type it in this in Desmos, I'm going to show you how to properly type this in Desmos for us to get an answer here. You would type in Y1 because the graph has Y1. Now we have to go down here to this keyboard, hit the ABC, and then hit this tilde. So then we would type in A, B, and then we have to take that to the X power. Hit this here, and then take it to the X power. Okay, now, the X power, remember, we're taking our X values from this table up here. You notice it's an X1 or X sub 1. So we have to change that X to an X sub 1. So let me hit that. So now that we have this here, you have to do one extra thing before we write out our answer. When you're doing exponential regression, you got to click on this log mode here. And then now we can write our answer out. So it'll be y is equal to 255.06. They say go, oh, they told us to have 5 digits in our answer. So we have 5 digits times, it'll be 1.0104, and we would take that to the X power. This would be our new equation. Yes, I did click on log mode. Yes, you have to click on log mode when you're doing exponential regression on Desmos. If you don't click on it, the answer that they give you will be incorrect. Okay, number 7. Based just on the base of the exponential in your equation, do you think this equation is likely to give a better estimate for the 2015 population than our first model? It says why or why not. Okay, so it tells us that the growth rate is, based upon this here, will be 1.04%. So we have a slower growth rate. And that will lower the chances of over predicting. Now it says use your equation to estimate the population in 2015 and 2050. Compare the 2015 estimate to the population you already found on the internet. Then search for a site that does population projections and see how your prediction compares. Okay, let's do this first. We have y equals 255.06 times 1.0104. Okay, now they want us to first do 2015. Now remember, this is from 1990 now. So our x value would be to the 25th power. So that would give us 330.35 million. And this is much closer to the 325.13 million. Now they also wanted us to do it to 2050. So it'd be y equals 255.06 times 1.0104 to the 60th power. So let me put that in a calculator. So 255.06 parenthesis 1.0104, close the parenthesis and take that to the 60th power. So this will give us 474.51 million. Now, on one of those sites, on Worldometer, they predicted that the 2050 population will be 400.85 million. So they think population growth will slow down more. Okay, so this is basically it from section 2.6. Now we want to mosey on over here to 2.7, which is on page 191. Now, just to give you a little outlook on this, we're only going to go up to page 195, and then we'll be done with 2.7. It says learning objectives. Decide on an appropriate type of model for a given data set. Model data with a linear or exponential equation. Research current data to compare to values predicted by a model. Now, if we look down here at the bottom, it says if you're like many students, you're concerned with the cost of attending college. It's certainly not a secret that college tuition has been rising rapidly over the last 20 to 30 years. But what about the facts? For that, we need some data. The table below lists the average tuition cost for all public American colleges and universities for a variety of school years started in 1981. Okay. So we know this is our 0 year, and all the other years will be based off of 1981. So what they want us to do first is to fill in this table. So all of those years. Now, if you want to, you can flip back and forth. Remember, everything is from since 1981. So these are all the years since 1981 that we have in that chart. So let me see these values in here. Let's see, 22, it's 92.47. $256. All right, almost done here. So 14,000. All right. So these are all the figures. They told us to fill in the table of values using the information in the last table, which we did. These are all the values from the previous page, but we converted the years since 1981 to since 1981. So instead of 1981, we put 0. Then it's supposed to be 1991, and then 2001, then 2002, and so on. Okay, now they want us to draw a scatter plot of the data in your table. Make sure you choose an appropriate scale for each axis and clearly mark that scale on your graph. Okay, first of all, we know these are the 0 values. We go from 0 to 30. If you count here 1, 2, 3, 4, 5, this will be 5, 10, 15, 20, 25, 30, and then about 34. So we will have more than enough room here. So we could go by ones here. So this will be 5, 10, 15, 20, 25, 30, and then we go up to 34. Now up the side here, we start at 2,663 and go up to 14,294. 292. And so what we have here down the side, we have 1, 2, 3, 4. So this would be 4, 8, 12, 16. So we could go by 100s here. Oh, I'm sorry, no, by 1,000s here. So this would be 4,000. This would be 8,000. This would be 12,000. This would be 16,000. So we know that this is money. Okay, so now we want to plot these points. 0, 26, 63. It's a little bit closer to 3,000. So we'll go to 10, 51, 38. So let's say 5 about here. Then we will go to 20, which is 8,022, which is about here. Then 21, it'll be 8,502, which is about here. 22, it's be 9,247, which is about here. 23, see 23 will almost be close to 10,000. 24 is a little over 10,000. Let's see, almost halfway between 10 and 11. 25 would be a little over 11,000. 26 would be almost in the middle here. 27 would be a little over 12,000. 28 would be close to 13,000. 29 would be in the middle, just about. And then 30 would be a little over 14,000. So there's our scatter plot. So now we move on to the next page. It says, based on your scatter plot, which type of equation do you think will most appropriately model the tuition data, linear or exponential? Okay, well, if we look here, points seem to line up pretty good. So, if I was to predict it, I probably would say that it looks like linear would work. Now it says, using a graphing calculator or a spreadsheet, find the linear equation of best fit for your data. Round all coefficients so that they have 5 digits total. Okay, so basically, what they want us to do, and we can go up here to this table so we can keep the same, so we don't have to reinvent the wheel as far as the table is concerned. All right, so we have 0, 10, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Okay. Now we have to type in the values over here. So we have 2663, 5138, 8022, 8502, 9247. Okay, 9864. 10,454. 11,049. 11,573. 12,256. 12,804. 13,564. And finally 14,292. All right. So now we put in these values. Now, one thing I like about this, even though we're not looking for this right now, is that when we put these values into this chart here, the exponential equation automatically updates. That's why I didn't get rid of it. So let me put in a linear equation. All right, so we know we would put y sub 1. We need that tilde. mx1 plus b. Then we have down here our equation. So we will have y is equal to, our m is 385.66x, because remember we're only supposed to have 5 digits here, plus 1501.2. All right, so this is our linear equation. Now it says graph the line of best fit in your scatter plot on screen. Based on the graph, how well do you think your model fits the data? All right, let's take a look. Now I'm going to have to zoom in a little bit. Okay, it doesn't look like my model fit the data that well. No, it doesn't look like it. So, because this red line is what this model is, and you notice the blue line, well, okay, don't worry about the blue line. Let's look at these points. Where are, okay, I have to scroll in here. Maybe take it out just a little bit. Hold on, let me turn off. This is throwing it off by seeing this graph. It looked like I need to change my table a little bit. All right, let me see something here. The axis. I think the x-axis is pretty okay. It's the y-axis that I think needs to be changed, because we don't need negatives for the y-axis. Really don't need it for the x-axis either. Let me go from 0. So the y-axis is supposed to go up to 14,000. Oh, this keeps jumping a little bit. All right. So let's see if we go from 0 to, let's say, 15,000. All right. Now the x-axis, we can go from 0, let's see, to 40. All right. Yeah, that looks a lot better. Okay, now this is our line, the linear line, and then this right here is the points. It doesn't really hit the points that well. So it says, based on the graph, how well do you think the model fits the data? It does not seem to fit the data as well as I thought maybe just to zoom it out just a little more so you can see that it's not really hitting that many points. Okay, it says, what is the correlation coefficient for your equation of best fit? Does this change your perspective on how accurately the model fits the data? So if we look here at our R value is 0.9709. Okay, so we know that this is real close to +1, but I would say that it really doesn't change my mind. No, it does not change my mind. But it does show that it is a good correlation. Now, let me explain this. Okay, if R was equal to 1, that means that it will perfectly fit all of the points. But since R is equal to a number close to 1, it just lets me know that this isn't the best, but this is still a good fit. So it really doesn't change my idea about this, because I thought it would hit a little bit more than what it did, but I still thought it was still a good graph. Okay, now we come to the back here. It says, write a description of what the slope of your linear model tells you about the growth of tuition since 1981. Well, if we write out our equation, oh, you know what? I didn't pull the camera back up. Okay. Okay, can you all see both screens now? Okay. All right.
Yep, I can.
Okay, thank you. Okay, now it says write a description of what the slope of your linear model tells us about the growth of tuition since 1981. Be very specific. So this was our equation that we had got off of Desmos for the linear model. I think it was, wait a minute, let me look here. 15.1.2. Okay. So this was our equation that we got from the linear model. So the equation estimates the average tuition goes up every year $384.23. Because remember, your slope is basically what basically the pattern of it. It shows whether something goes up, whether something goes down. So it's showing that it goes up by $384.23 per year on average. Now for number 8, it says now use your calculator or a spreadsheet to find the exponential equation of best fit for the data. Again, round all coefficients so that they have 5 total digits. Now, remember how I told you here, when we did this here, it automatically updated this equation. So when we typed all of this here, the exponential model we had here automatically updated. So this will be our equation. Okay, someone said they don't see how I got the 384.23. So let me go back up here, down here, I'm sorry. Okay, when we did the linear model, if you go back, hold on one second. Okay, what we needed to do, we needed to go back to the previous page for problem number, I believe it was problem number 4. It says use a graphing calculator and it gave us this equation here. Oh, you know what? I made a mistake. This is supposed to be 385.66. Thank you. X. So it's supposed to be 385.66x. So this should be $385.66. And it was based off of the previous problem that we had on the other page. Or you could have looked down here. 385.66. All right. Now they want us to use this here. This is already set up. So now we can write out our equation. We know our equation is y equals ab to the x. Y is equal to a is 2,757.02 times 1.0566, all taken to the x power. Now let me explain something here. The reason why I have 6 digits here instead of 5 is because this would end up just being 0.0. And typically we don't like to leave it as a 0.0 if we could avoid it. So we have these values here. It says graph the exponential equation of best fit and your scatter plot on screen. Based on the graph, how well do you think your model fits? Okay, listen. This is what we're going to do. Since we have the scatter plot here, let me show you this. All right. I'm going to turn off this linear model. So that line is gone. I'm going to zoom in a little bit so you can see the points a little better. Okay, well, let me do it one more time. Okay. Now, I'm going to turn on the graph here. So if you notice here, this graph looks a lot better. And then I could turn on this graph here and you can see the difference. Okay, so now we come here. How well do you think your model fits the data? The model seems to fit a lot better than the linear model. Okay, number 10. It says, write a description of what the base of the exponent in your exponential model tells us about the growth of tuition since 1981. Okay, now, this B here is considered the base. This is the base. So to find out the growth, this is what you do. You would take this value, subtract 1 from it, be 0.0566. Then you will convert this to a percentage. So you'll move this decimal 2 places to the right. So it'll be 5.66%, which would be the growth rate. So 5.66% is the growth rate of tuition. So that is how you would get the growth rate. All right, now, number 11. It says, what is the correlation coefficient for your exponential equation? So the R value is equal to 0.9983. Much, much closer to 1. Does this change your perspective on how accurately the model fits the data? I would say no, because it is so close to 1 and the graph is very close to perfect that it doesn't surprise me. Okay, number 12. Based on all of the work we've done in this portion of the lesson, which model do you think is the best choice for modeling the tuition data in the table? Why do you feel this way? Okay, I would say exponential is the best because the graph looks more accurate and the correlation coefficient is higher. So those would be the two reasons that I would give why that's better. Now we are done with 2.6 and 2.7. Do you all have any questions? Do you have any questions? Okay. Now I will be sending out an email concerning the midterm. I'll be either sending it out today or tomorrow. I believe for the midterm, we may have to set up a time in class for you all to be able to take it because I don't think this program that we have is going to work that well, but I'm going to check it out. But I will let you all know between today and tomorrow how we're going to have the midterm set up. So basically, that is it from today's class.